So what does it mean in geometry for two polygons to be similar to one another? Because we spend so much time thinking about triangles, and if you're familiar with how similarity works for triangles, you might have sort of a narrow idea, a narrow sense of what similarity means. In fact, similarity is a quite demanding requirement. It requires two different things. It requires that the angles of our polygons be congruent to one another. So the corresponding angles have to have exactly the same measure as one another. And it also independently requires that the corresponding sides of those polygons stand in equal proportion to one another. So to unpack that a little bit, say I have these two polygons, and I'd like to define what it means for these two polygons to be similar. So I'm going to label these what are these? Seven-sided, so they're heptagons. I'm going to label the first one with vertices A, B, C, D, E, F, and G, and the second with vertices A prime, B prime, and so on up to G prime. And I've labeled them in such a way that I'm going to set it up so that each of the vertices in the figure on the left corresponds to its corresponding primed vertex on the right. So A and A prime are going to be corresponding, B and B prime are going to be corresponding, and so forth. So the notion, the intuition of similarity is that these are two polygons that have the same shape, but they might have a different size for whatever that means. So the two criteria for similarity encapsulate each one of those pieces of that statement separately. First, we end up with two figures that have quote-unquote the same shape because the corresponding angles in these figures are congruent. So these two figures will be similar in part because the corresponding angles having the same measure gives us the same shape going from one of these to the other. So that means that, for example, the angle at A, GAB, and the angle at A prime, G prime, A prime, B prime, have the same measure. So those are congruent angles. But then the angle at B also has to agree with B prime, C with C prime, D with D prime, and so on and so forth, all the way up to G and G prime. So every corresponding pair of angles has to be congruent. That gives us two figures that have quote-unquote the same shape. But it turns out that for most polygons in geometry, that by itself is not enough to guarantee similarity. In fact, even for four-sided polygons, quadrilaterals, we can construct an example of two quadrilaterals that have congruent corresponding angles, but which do not have equiproportional corresponding sides. So we need these two criteria to be separate, because most of the time they don't guarantee one another, even though we will see that they do for triangles. So having the same shape is guaranteed by criteria 1. Criterion 2 will guarantee that they have a similar, a comparable, but not necessarily equal, size to one another. We do that by saying that the corresponding sides are equiproportional. That if I look at the ratios of the lengths of all the corresponding sides in these polygons, that those ratios will all agree with one another, no matter which pair of corresponding sides we choose. So for example, if I pick the length AB on the diagram on the left and A prime B prime in the polygon on the right, let's suppose for the moment that the length AB is 4 and A prime B prime is 6. Well, if I divide the former by the latter, 4 divided by 6, I'm going to get a number, 2/3. That tells me the ratio of the length of the side AB to the length of the side A prime B prime. We might say that the length of AB is 2/3 as long as the length A prime B prime. What it means for corresponding sides to be equiproportional is that I should see that same 2/3 proportion for every other ratio of corresponding sides in these two figures as well. So if AB is 2/3 as long as A prime B prime, we should also, if these two polygons are to be similar, have BC be 2/3 as long as B prime C prime. So if BC is 5, for example, B prime C prime would need to be 7.5. Because then if I divide those two numbers, 5 divided by 7.5, that ratio is also equal to 2/3, and so on, and so on, and so on. So every pair of corresponding sides that we compare by taking their ratio, we need to get the same ratio, the same proportion for each pair of corresponding sides. That constant, which we're labeling here as K, is often called the constant of proportionality that relates these two similar polygons one to another. So that number in this case is 2/3, and we might put that into a sentence by saying that each of the sides of my polygon ABCDEFG on the left is 2/3 as long, or 2/3 times as long as the corresponding side of the polygon A prime, B prime, C prime, D prime, E prime, F prime, G prime. So having the same shape but potentially different size is encapsulated in our definition of similarity by insisting that the corresponding angles of our two polygons be congruent. So the angle measures all have to agree on corresponding angles, but then also that the corresponding sides in these two figures are equiproportional. That if I take the ratios of corresponding sides, no matter which sides I choose from my two polygons, that the ratios of those corresponding sides will always give us the same number, which we call the constant of proportionality between these two similar polygons.